Welcome back. So lecture 8 will discuss model-based IR. Uh, I know that Carla has given you more of a high-level overview of a lot of the IR algorithms. Um, in these subsequent lectures, I would like to go into more details on the more fundamental topics based on the textbook by Sutton and Bartle, which is available on the in the Canvas and also online. So this is the classic IR textbook uh, that is written by the founders of the field, and it is actually quite readable. It's not a very dense technical book. It actually has lots of interesting examples that you can easily follow. And uh, these so Sutton, so Professor Bartle has retired. And Sutton is still working now in University of Alberta. So they have a specialization on Coursera, which consists of sequence of 4 courses, and it's based on the textbook. And I'll take some much of my material from this online course, and I highly encourage you also to follow this Coursera course. And also, besides this textbook, I also introduce research work on applying IR and IR to autonomous driving in my future lectures. So in this lecture, I will discuss the books. So I skip the multi-armed bandits because it's not really relevant in our context. So I will discuss MDP and dynamic programming, basically chapters 3 and 4. And later I'll discuss sampling-based methods such as Monte Carlo and TD learning and so on. So let's start from the basics. MDP consists of set of states, start state as 0, set of actions A, transitions. The notation can be different. Basically, it's transitioning from state action to a state prime, next state, and rewards and discount gamma. So the term Markov means that next state only depends on current state. So you have a long history of past state actions, and it's only dependent. The conditional probability distribution is only dependent on the current state ST and current action AT. So given the present state, the future and the past are independent. So there are policy and value function and Q value function. Uh, Actually, I'll fix the slides later. So MDP search tree, each MDP state S projects a search tree starting from it. In general, both policy and environment may be stochastic. So from a state S, you may have a policy, which is a probability distribution over possible actions A from state S. Of course, you may have a deterministic policy as a special case. Environment may be stochastic. That is, if agent takes an action A in state S, environment gives probability distribution over reward R and next state S prime. So from a state, the agent, the robot, plans an action. Say perhaps it goes right in this position. And then the environment gives you a next state and a reward. So it's kind of like a two-player game. The agent plays a hand, issues an action, and the environment plays back and gives you the next state. So either player can be deterministic or can be stochastic. So the agent may issue a action A1 with probability half, A2 with probability half, and environment may have unpredictable unknown factors that may lead you to different S prime for the same SNA. So you must keep this tree in mind when you are looking at the Bellman equations. So in terms of a reward, what if the game lasts forever? So do we get infinite rewards? So nothing lasts forever. So one solution is to have finite horizon. So limit the depth of the tree. So terminate the episode after a fixed t time steps. So the t is predetermined. So this approach gives non-stationary policies, which means that the policy is dependent on the time left until the end of the episode. So for example, life has a limited length. It's a finite horizon game. So if you know you're going to die tomorrow, you're likely to take very different actions today than if you know that you will die 50 years later. Your priorities will change. So that's a non-stationary policy. So discounting is a more widely used, more common approach. So you use a gamma discount factor, and the further away, more remote rewards are discounted more. So the future is uncertain, just like your money in the bank. So based on inflation, it loses value gradually. So if you're given a choice of earning $1,000 today versus earning $1,000 20 years from now, obviously uh, the today's money is worth more than future money. So that corresponds to a discount factor. So smaller gamma means smaller horizon. That is a shorter term of focus, more short-sighted. Larger gamma means that you're more far-sighted. Another approach is absorbing state. That is guarantee that for every policy, a terminal state will eventually be reached, like overheated for racing. That's one example. So discounting, so why discount? Think of it as a gamma chance of ending the episode, ending the process at every step. So at every step, you have a particular a chance of exiting, of leaving the game. So if gamma is large, then your chance of staying in the game is high. So you're likely to keep playing. If gamma is small, uh, uh, gamma is the discount factor. So small gamma is smaller horizon. Uh, I think I got it wrong here. Should be 1 minus gamma. So if the gamma is 1, then you always go. You never stop. Right? If gamma is 0, then you essentially die after the first step. Yeah, it's 1 minus gamma. So for this example, if you have a sequence of rewards 1, 2, 3, then the cumulative reward is less than 3 to 1 based on the discount factor. So here's a discounting example. You have actions east, west, and exit on the one-dimensional grid, and you have exit states A and E. A has reward 10, and E has reward 1. The transitions are deterministic. So for gamma equal 1, so optimal policy in every state is always moving left towards state A with the high reward. So because say from state D, you have a reward of going west is gamma cubed times 10 because it takes 3 steps to reach state A and get reward 10. 1, 2, 3. Yeah. So it's larger than going east. For gamma equals 0.1, you can calculate the reward. Did I get it right? So state D, I think I got it wrong. Sorry. I'll fix it. So state D, it should go east. Yeah. So based on the discount factor, if we go west from D, then you eventually you get a reward of 0.01. But if you go east, you get a reward of 0.1. So from D, you should go east. But from C, you should go west because you have gamma squared times either 10 or 1. Obviously, going west is better for C. So the policies of B and C are correct, but policy of D should go east. So for which gamma are west and east equally good when in state D, you can solve for this equation and get gamma equals 1 over square root 10. So this means that this notation means that in this state, both actions are equally good. So I have this big picture table here. I'm not expecting you to understand it right now, but I think you should understand it after I finish my lectures. So high level, the task can be prediction where you compute the value function for each state for a fixed policy pi, or control, that is, you're trying to optimize the policy to find the pi star. And you may have algorithm with known MDP that's a model-based planning. And then you have these series of methods: policy evaluation, policy iteration, value iteration, Q-value iteration. And then for unknown MDP, then it's model-free. You need to use sample-based method like Monte Carlo learning and TD learning and Q learning. So in this lecture, I will discuss this column here with known MDP. So with known MDP, we can use dynamic programming to solve MDP and find the optimal value and policy. So here's the Bellman expectation equation for state value function and for action value function. State value function is the expected value starting from state S and following policy pi. So it has expectation over actions expectation over the reward and next state, current reward, and gamma times next value function, v pi s prime. So it's expectation over policy pi, given fixed policy pi, a big RT, which is defined as expected value at current time step t, for typically for simple grid like problems, small games, for each state we associate a reward. So if you enter the state, you get a reward. But in general, the reward may be dependent on the S prime. So from the same S and A, depending on different S prime, you may get a different reward. So that's a general case. But most cases in this lecture, we only have a single reward for the same state action. So this expectation typically it just means RT, big RT is equal to small r. But in general, it's an expectation over all possible reward and next state. So it's expectation over pi, the big RT, current reward at time step t, plus the gamma discount factor times the v pi of the next state, st plus 1. So the big S is a random variable with probability distribution. Small s is a particular state. And then you have the Bellman expectation equation for action value function. That is Q pi SA. That is the expected value starting from state S, taking action A, and then thereafter follow policy pi. So you take action A, and then you follow pi. So it's equal to expectation over policy, the current reward RT plus gamma v pi st plus 1, except the conditional probability has on the right, on the condition part, you have st equals small s and at equals small a. That is at the current time step, you take an action that's specified. And then in the future, you follow the policy. So the relating these two, v pi s is equal to sum over action, the policy pi a given s times the q value function sa. And the q value function is can be written as the expectation over r and s prime, the current reward, and the gamma times v pi s prime. So that's the Bellman expectation equation. Bellman optimality equation. If you compare these two, okay. So if you compare these two, the only difference is you have a max over A for V star as the optimal value state value function, and max A prime Q star here for the optimal action value function, as opposed to the expectation over A for the Bellman expectation equation. So Bellman expectation is taking the expectation over all possible actions to calculate the value function, whereas the Bellman optimality equation is doing a max to find the optimal value functions. So if you write out this recursion, so the notation here is slightly different. but you get the idea. So the value function from S is argmax of A1. From S1, you take action A1 plus gamma times the subsequent next state S2, and you have a transition probability. This transition here is corresponds to the notation above as P R S prime given SA. And then inside, you have a max A2 and the next state S2 and action A2, and then gamma times the next state S3 and A3. So it's an infinite nested recursion. And if you cut the recursion this way, you have the Q value function. If you cut the recursion at a different point, you have a V value Bellman optimality equation. So relating the V star and Q star, you have V star S is max A for Q star SA, and Q star SA is expectation over R and S prime of R plus gamma V star. So this can also be seen from this figure here. So V star S is max action over Q star SA. So inside of this is the Q, and then you take the max, you get the V over max over A, you get the V. And starting from V to get Q, you need to do more. You need to add up the current reward and the gamma times the future reward. So I would highly recommend you to stare at this picture for an hour and memorize it in your heart. So backup diagrams are very helpful in understanding Bellman equations. So look at, you can think of the big green circles as the action, as the agent in state S, with either a expectation for a fixed policy or a maximum for optimal value and policy. So at this state S, the agent can take an action A based on policy pi A given S to reach this blue state. The blue state is a so-called state action node. So and then it's the turn of the environment to play the other hand and provide the agent with the reward R and the next state S prime. So this blue state is never is not a real state. It's more of a helpful construct to help you think of Bellman equation. So the real state transitions from a green to green, but it divides up the transition into two parts. One is from a green to blue, where the agent has the initiative and takes an action, and from blue to green, where the environment has the turn to take to give the reward and move the agent to a new state. And the backup diagram means that when the Bellman equations are backing up from bottom to top, So it's better if you look at the backup diagrams along with the equations. So for example, let me do a temporary move Bellman optimality for V star. So so let's look at this equation here. So from V star S prime, this guy, you multiply by gamma and add the reward R, you come up to the and take expectation over all possible reward and next state. So whenever you have a no mark here, it's expectation. That's this part. And then you go up and take a max to get the V star S. So that's how you back up from V star S prime to derive V star S in this backup tree. And for Bellman expectation equation, the only difference is that now you have an expectation here, not a max. So for the Q value functions, you have a different view. Now you're starting from SA state. It means that you have already taken an action or decided to take the action A. Now you're just waiting for the environment to give you the next state S prime and the reward. And from this point, you can do a backup from Q star S prime A prime. You can do a max over A prime, and then back up. That's the expectation over here. That's the expectation, and then you get the Q star. Similarly for the Q pi, and both levels are expectations. So the agent only has choice of different actions for the state from the state nodes, that is from the big green nodes, and then from the blue at the blue nodes, the environment has the initiative. The agent loses control at this point. So therefore, the agent can take a max to pick an action that maximizes the expected reward. But at the blue node, it's always expectation. The environment is not under our control, but our action is under our control. So that's why you may have max for the state nodes, but only expectation for the state action nodes. So any questions on the Bellman equations?
No question, but maybe I can take some time for the lab. So,
yes. Yes.
There's no hurry, but if it's a natural break for you.
It is actually.
Yeah. Do the students want some minutes break, or should we go?
I guess we just had a break half an hour ago, so I think we can continue.
Okay, that's good. So, so how do I share my screen? So I will going to take like 15 minutes to explain a little bit about Lab 4. It's not so difficult, but there are things to learn from that as well. So, and I am working with a future Lab 5 with the car racing stuff. And I got it to run on Colab. but it stores a lot of files. Yeah, it learns, but you don't know what to learn and how it learned and so on. So I need to take care of the result from the learning from the car racing to present it in some way. So I'm working with that now, so we hope we'll be ready in the beginning of next week. So we added this extra little lab 4 while waiting. So I can share my screen then maybe. Do you see my screen by now?
Yes.
Yeah.
Good. So we have on the side here, we have the assignment, and we have the new assignment lab 4. And instead of adding a lot of text here, I made a separate page here. And the idea is to play around with this highway environment. And that is done by using the Colab environment from Google. So we don't have to install anything, we just open those things. So we do this by just right-clicking this, save link as. So you download this file, highway planning, and this parking model to your local drive. And then you start Google Colab by clicking here. And then you press File, Upload Notebook, and then you select Upload, select File, and then you have hämtade filer in Swedish, and then we go for this highway planning, which is the first one, and open. So then it will open this in Google Colab. So there is actually on the home page, if we open that follow link as well, there is a opening Colab link at the GitHub page, but this doesn't work because it's old code. So there will be some errors. So I made some modifications to make it work on a new Colab. So you either can run by pressing those things, or you can run by pressing run time, run all. So now this with exclamation marks is commands out to the Linux system. And these are Python things. So it simply installs the stuff from this highway environment. And at the same place, there is also a library of agents which can be used. And then there are some more stuff. So we see it is kind of fast. And then after some time, it starts running. So it makes this, is this screen, is the big enough? Maybe I make it bigger for you so you can read. So it's a gym environment. So we have highway 1. And we also have a wrapper which record a video when interacting with this environment. So we capture a video. So we then run our agent on this environment. And then we take an action and then we run this for some time. And then we close and then we show the video. So we see now it's running. So this T range is just this little illustration. So we know it's haven't been stuck into something. So after some time, we will see a video. And we see also what kind of agent is selected here. And you can see those agents by clicking, for instance, this button. Let's see, you can do that from follow link. So we see there is a collection of different agents. So I don't want to go into the detail of all these, but we have learned a few, and you should know there are many more different kind of agents which are good in different things. And in this case, I think we have this deterministic open loop planning. No, optimistic planning for deterministic systems. So here we see the idea is when this method is good, reward shock to achieve a polynomial rate on regret, which is how bad it is compared to the optimal things. And it's kind of efficient in numerical experience. So it kind of saves CPU time. So you see there are other algorithms have other advantages and maybe disadvantages. So if you want, you can read this scientific paper, but there's no need to. But if you're curious, you can have a look at it. So it's written by Jean-François Rennes and Remy Munoz. And Remy Munoz happened to be a friend of mine. Let's see if I can. He is actually the boss at Google DeepMind in Paris, the only European office nowadays. So be kind to him. So here you can have some introduction how it works. So it's a sequential decision. So you have to decide how to turn this vehicle to avoid a collision. And then, yeah, you can read this maybe in detail for yourself if you're interested. But the basic idea is that you have some kind of tree with possible actions, maybe similar to that what Songwa showed us recently. And then you kind of explore the most promising nodes, which seems to be the best actions, but you only kind of guess in an optimistic way by hoping that this is true. And this shows that it can be a good way to select those. And the idea is also that you have an upper bound. See, upper bound to the tree. That means upper confidence bound. So we know a little bit about how good or bad these actions can be. So this is how to make things if you have resources which are limited. And that's often the case if you're running a car in a traffic, you need to have a quick response, and maybe the car CPU is not so powerful either. So you have to be a little bit careful about those things. You maybe not find the best action, but at least you find it in time. And then we go back to the Colab stuff. And now it seems to be ready. So we can see how it behaves here. So it's supposed to drive in the right lane, lower lane in this case. And then when there's a car, it has to change lane and then go back again. So that's the basic idea of this agent. And you can learn about the environment as well. If you look at, you can maybe click just environment stuff here. So then you see the GitHub for the environment, and there are many of them. You have this highway, you have another merge where you try to merge in a road junction, and you have the roundabout where we try to avoid collisions. And there is the parking task, which will be the next one. You have a goal parking lot you're supposed to reach. And there is another with intersections, so you have to negotiate with other cars to not collide. So there are some different kind of environments to play around with and some different agents as well. And the vehicle kinematics is a typical bicycle model, simple one. And the control for the longitudinal, the speed, acceleration. And then you have a lateral model to change the lane. So we can have a look at the repository for the environment. We can see, so you have the highway environment. You don't have to do this for doing the lab. This is just for extra information. So if you look at the environments, and in this case, we have the highway environment. So then you can see what kind of actions is available and what kind of rewards. when colliding, you get -1. Driving rightmost, you get 0.1. If you're driving at full speed, you get reward. And then if you change the lane, you don't get any reward. So in this case, the agent requires the reward to be within the 0 or -1 to +1 range or something like that, I think. And then you have the actions is change lane and so on. We see the actions maybe was, you see, you here you inherit from abstract environment. So you can go to the abstract environment to see what actions are there. Really, don't know if they're in the common. Yes, abstract. So you can see here are the actions: lane left, lane right, idle, do nothing, go faster, go slower. So these are the 5 actions which you can select. So they are kind of discrete. And this is how the rendering and so on is done. So you don't need to have this all detailed information, but my idea with this lab is to play around with, maybe at least try the basics, and then if you have the time and feel it's fun. Oh, sorry. So you can maybe try another environment on your free spare time if you want to learn more, and you can try another agent. So this agent we try for this one is this, which we looked at a little bit quick. And then the other task is to run the parking model, and then we have a runabout as well. So we go File, Upload Notebook, and then we select the other one, High Parking Model. So here we have model-based reinforcement learning. So here's written a little bit detail about unknown systems, and the idea is to first learn the model and then plan based on those models to compute optimal trajectory. So you kind of try to learn the model, and that is because you don't have so many rewards when you try to do your parking stuff. So you need to make it in some better way. So this parking system, if we also run this to save some time, it's the same environment, and then we have to install that. And then there's some stuff with videos. So we have this parking, we store this as a video, and then we just sample for some time, and then we select actions. And then after the sampling, you have collected the experience, and then you try to use that to build a dynamic model. And this is a standard LTI control model. And then you fit the model to the data from your experience, and then you try it. And here you predict a trajectory to be able to run this. So this was in short what you're supposed to do. So I hope you can study the code a little bit more in detail and so on, and answer some simple questions. But the basic idea is for you to play around with this environment, which is, I think it's interesting from a parking point of view. And also, if you have the time or in the future, you might play with some other agents and some of the other basic environments here. Maybe you will try the roundabout yourself or the intersection stuff. And then you might need to change the agent. So are there some particular questions? You see now how this is training. Then we see this error goes down after some epochs. And then we can see different trajectories, how to plan those things. And then we have reward stuff. So we need to read this a little bit in more detail if you're very interested, but it's not absolutely necessary. It's just to engage your curiosity a little bit. So you try to plan, and then you can visualize a few episodes with this CEM cross-entropy method planner. So this is kind of advanced research stuff. So you don't need to learn this. There will be no exam question on these advanced methods, unless Songhua has presented them. I don't know. Have you gone through
No,
something?
I haven't read this GitHub yet. It seems like they have a lot of good publications.
Yeah. So for this, as a lab, it's more like you play around with it and then you see, does it seem to park? Not so very good all the times. So this can be useful for yourself when you try to, if you drive your own cars, to see how would you drive to park in that particular lot. And then we have another little movie in the field of safe reinforcement learning, which maybe Songhua will present a little bit more. And then we just click this one. So we will see a small video about this roundabout. So we try to drive fast and then we can have dangerous situations. We see very close to collisions now and then. So if we have some small model errors, so we might collide. So there are some things about this. So you don't need to know the details of how to actually do this or read the reports, but it would be nice for you to have some, just a basic understanding of the problems also. So you can run things here and so on if you want to. But that is about lab 4, and you only need to kind of reply to those more or less simple questions. So this should be just one page of text or so. But of course you can write some extra text to make it more, oh, sorry. Yeah, you got some introduction to robust control. So this was a very quick run through of these different environments, and there are a few agents, as I mentioned. So you might have a look at other agents as well if you want to look this planning, like value iteration, which I think Songhua presented just recently. So we have this Bellman dynamic programming from 1957, so on. And then these other methods like Monte Carlo tree search class of. So here you have, yeah, how about the backups and so on. Maybe Songhua will talk about that later, I think, or I hope. So if you have a Monte Carlo approach, that's kind of opposite to the value iteration. So here you more or less drive and see what's happening. So after the episode, you kind of learn, while this maybe learns while doing the episode. as I understand it. So is there maybe some questions?
Hi, yes. It's about the environment with the crossings and with the cars. What is the complexity of the models that those environments require? Like, for example, is a tabular model sufficient, or should it be something more complicated?
In this first approach, there was a decision tree, I think. So there was a tree, so you put your discrete actions, there were like 5 actions. And then what is the information this vehicle get about other vehicles and so on? That's interesting. I guess that was the question of you.
Because, well, yeah, more or less, but because, like, my intuition is that if the initial state and the goal state, they might change by a different iteration of the same environment, like a tabular representation, it would not be appropriate, let's say, like it should be enormous.
Yeah. So then, yeah, we can have a look at the agents wherever we have this environment. We can have a look at this agents type. So we can have a look at the agents in detail. So if we look at which one we selected here, I forgot.
Yeah.
It was a tree
Yeah.
search.
Okay.
Tree optimistic. So then we can have a look at how this runs. Leaves. They have leaves. There's a kind of tree, and you search this tree, some leaf values. So it seems to be discrete at least. And then you get actions from a list here. So we have a list of actions with probabilities, and you select the action with the highest probabilities by random selection. And here we expand the possible actions. So if you are in a state and then you try to see what kind of actions is possible in this state.
Okay.
So it seems to be maybe not a grid, but a discrete tree. I don't know all the details, but it looks like you select actions from some kind of action tree.
Okay, not a tabular representation, but still like discrete is like sufficient.
Exactly, but this, of course, this tree, I guess it can grow a lot. So if you plan a long time ahead, then maybe this tree will be very big. So there will be a problem to find the best branch in this tree.
Mm-hmm. Okay. Yeah.
So that's my basic understanding of this.
Yeah, no, it was this. So yeah. Discrete, but not tabular. Yeah.
And it doesn't seem to be any deep reinforcement learning, so it's just basic reinforcement learning. I don't know if it has some deep Q. So I have some, I don't know. Some kind of DQN agent, but it's just a base class, but maybe it needs to be implemented in some way in the details to get this deep tree or deep reinforcement learning agent.
Mm-hmm. Okay.
maybe, I don't know, PyTorch. Yeah, so here we have this D2N. So here is a real agent based on the space class abstract. And here is this Bellman residual stuff, target transition table, batch values, load, and so on. So yeah, so you can look around a little bit in your favorite agent topic. Some more questions? So then we go back to Songua maybe. Should we have some more detail about the selected agent? I think I will, when we get this car racing to work, because that agent is kind of interesting and very useful, because that agent collects data from a picture. So now these agents in this lab 4 is mainly agents with like a few sensor data, like distance sensors or something. But in the last lab, we will look at pixel images. So that is how to drive a car based on video information. So that is kind of fascinating, I think. Some of you were on the mechatronics course last autumn, and then we had pictures where you can recognize situations, if the road is turning left or turning right and so on. And then we kind of used the deep learning net to recognize a situation. Oh, this is a road turning slightly to the right situation, and then the car was turning slightly right. So we used that, but they didn't learn. So we as a programmer had to decide if it's slightly turning right, then the car should turn slightly right. And then the image changed in the car's camera, and then you maybe looks like the car goes straight, and then you turn back into straight line. It worked, but not so good at the mechatronics course. They were running quite slow and so on. So maybe this reading directly from the video and learn might work better. But it's also really very demanding. And that's the reason for problems with this car racing stuff, because we're going to use multiprocessing. And that is, if you have a CPU with 4 or 8 cores and so on, then you try to spread your calculation on these 4 or 8 or 6 cores to make it quicker. So that's a little bit problematic, but also very interesting to implement, I hope.
So Carla, is it easier to run car racing on Colab?
Yeah, I can provide you with a Colab car racing situation as it is today. But the problem is it stores a lot of files with JPEG images and so on. But after you have run this car racing, the files are gone. So there's not much use. It trains something, but you can't see what it's trained. So I will try to make those pictures, to put the pictures on your local Gmail account on your G drive. So after a run, you can study the files and the pictures and also the weights and so on to see how it works. Or at least we can add something in the end to the car racing example. So it at least shows the images or shows the video and so on. But there are some problems, because if you have like 8 cores storing files simultaneously, it seems like they collide sometimes, and there will be some file system errors as it works today. So I have to check it out a little bit more. So I hope I will make it work. Otherwise, if you run it locally, then Then you have the animations, and then of course you have the files locally on your computer, and then you can study the videos and weights and pictures and so on. But it's kind of complicated to install all these things, so it's a high risk you run into some kind of trouble. But I will give you an opportunity to a list of what you should install if you want to run locally. But if it doesn't work, you have the Colab version to fall back to, or use it just that if you don't want to install. And I don't know if you have tried PyCharm. So once you get into a little bit bigger programs, this Jupyter notebook is not so practical if you have many files and so on. So it's good to have a traditional development environment like IDE or Visual Studio or something else. So I think we have a look at that as well. So if there are no more questions, I'll leave back to Sungwa.
Yeah. So before I resume lecture, maybe we should take a break. I think people are tired. It's been a few hours. So let's resume maybe at 3:25. Okay, 3:25. See ya.
Okay, good luck, Sangwa.
Okay, thanks.
Thank you for the break also. So I will go to the other course now.
Yeah, okay, have fun.
Yeah, good luck to you too. But what are you going to talk about next Thursday?
Oh, I'm thinking, I'm discussing, so I'm following the textbook by Sutton Bartle to introduce in this lecture. I'm talking about chapters 3 and 4 on the model-based dynamic programming.
Yeah.
And next lesson, I'll talk about Monte Carlo and TD learning and Q learning.
Yeah.
So I know you
nice.
discussed this before, but I wanted to give some more insight into the internal workings, into the with some toy examples and so on.
Yeah, very, very good, because we have a just very quick look at those things. So it's very good. You take a deeper look. So that will be exciting. So you have also the new book, the version 2 book from.
Yes, I have it.
The... Okay, good luck. See you.
Okay, see ya.
Bye.
So would it be possible to give some like reading instructions from the book on what we're supposed to cover or what we are covering?
Which chapters you should read, you mean?
Yeah.
Oh, I see. Sure. I mean, I think you should read the whole chapters 3 and 4.
Okay. Well, I mean, if that's the case, so yeah.
Yeah. They're
okay.
not difficult to read, actually. Yeah.
Okay, great. Thanks.
Sure. I hope everyone is back. So I just changed the title of my slide. So you can download from Box. So originally I called it model-based IR, but it's not really accurate. So if you look at the book, I'm sorry, I didn't share my screen. So the book, chapters 3 and 4, is talking about dynamic programming based MDP planning. So it's not reinforcement learning because you know the model and you're planning based on a known model. Therefore, I changed the name to MDP planning. So if you do model-based reinforcement learning, then it has a additional step of learning a approximate MDP model and then planning based on the model. But now I'm only planning, I don't have the learning step. So okay, so let's so we discussed the Bellman expectation equation and Bellman optimality equation. So I marked important on these two slides because they serve as these equations serve as the basis not just for planning in this lesson but also for future reinforcement learning. So the backup diagrams should be combined with the equations to better understand the equations. Just to forecast in the future when we do TD learning or Q learning, the backup diagram will be a single line, whereas in here we have a tree. So we talked about value function, state value function, and the action value function. That is, one is VS, one is a QSA, either for a fixed policy or the optimal values. So the relationship among them is that you can always go from Q to V, either Q pi to V pi or Q star to V star. By this equation, that is V pi is expectation over A of Q pi SA. And V star is a maximum over A for Q star SA. So you can imagine this, again, look at the backup diagram. From the Q pi or Q star, you back up one level. Yeah, at this point, look at this. On the top, you back up from the blue node to the green node. That's the deriving from a Q to V. It's always feasible because you always know the probability, transition probability, and the max for the from the V node because it's under the actor's control. But in the other direction, from the green node, V node to the Q node, is not always feasible. And also, you can always get optimal policy from Q by taking argmax. So that is the max here. Whichever the action that leads to the max, you take that as the optimal action. Now, but in the reverse direction, it's only feasible for known MDP. That is, you know the probability of reward and next state from the current state and action. Can you go from V pi to Q pi or from V star to Q star? Because these equations involve this term P, which is the MDP model. So if the P is unknown, you cannot do this transformation. In here, you're trying to back up from the green node back to the blue node. Then you need to know the branching from the blue to green, the probability distribution, that is the environment property. So now it's not under the agent's control anymore. It's under the control of the environment. And the environment may be known if you have a simple grateful environment, or it may be unknown. If it's unknown, then you cannot do this derivation from V to Q. But with known, you can do the derivation, and also you can get the optimal policy pi star by this equation here. So all these equations here have this term of sigma rs prime over p, and that's the MDP model. And with unknown MDP, with unknown p, that is the model-free case, you cannot go from V to Q. You cannot get optimal policy pi star from V star. So Q function contains more information than V function. So if you're doing control, that is, you're trying to optimize a policy, that's why for control and you don't have a model, Q-learning is the way to go. That's the most widely used learning algorithm for learning optimal control policy. For Monte Carlo and TD learning, you get a V, but this V is not useful. V pi is not useful unless you have the MDP model for control. But just for policy evaluation is fine. So let's look into a policy evaluation. It's also called the prediction problem, as opposed to the control problem, which is to find the optimal policy. But here we're given the policy pi, and we're trying to estimate or predict the value function v pi or q pi. So so you just solve this Bellman expectation equation for state value function either analytically or by iteration. So if the system is small, you can solve the Sala equations for small systems efficiently. But if the system is large, by large I mean millions of states, then perhaps your solver will run out of memory, and then you need to do the iterative solving. So if you look at the set of equations, number of unknowns is equal to the number of equations and equal to the number of states. So they can be solved. So here's one example of a small great world. Agent has 4 states. They can take action west, east, south, north. So it always moves to the next state in the movement direction unless it is blocked by an obstacle, which is the wall. By the wall. There's no other obstacle. Suppose the discount factor gamma is 0.7. So it's a deterministic environment because the agent knows what his actions will lead to based on his action only. Environment has no non-determinism. Suppose the policy is random. That is, you have 25% probability of going to either of the 4 directions. So you instantiate the Bellman expectation equation to have this. So that is expectation over action, then expectation over reward and next state. So from state A, it has 4 possible actions. If it goes west, so if it goes east, it gets a reward of +5 and goes into state B. So its equation R plus gamma V pi S prime is 5 plus 0.7, the discount factor, and V pi of B. And that's with 1/4 probability. And then if it goes south, it has it arises. So first of all, the inner expectation is always 1 because the it's a deterministic environment. Maybe I should write something here. So it's always 1. So the expectation is only over the actions. So that's for east action, you're going to B, and for south action, you're going to C, and C had the action has reward 0 plus 0 here. So if you're going to B, you have a +5. And that's 0 plus 0.7 times V pi of C. And then if you go north or west, you always you hit the wall and you stay in where you are. So you get reward of 0, that's the self-transition, plus 0.7 times V pi A. You go back to A. So that's the instantiation of the Bellman equation for the A state. And for B state is similar. So you are, I'm sorry, I think I got it. Oh, that's okay. So for 2 directions, north or east, you have both have 5 reward self-transition. You're hitting the wall. And the next state is still B. So the weight is 1/2 because you have 2 directions with the same behavior. And then if you go west, you have reward of 0 and go into A. And if you go south, you have reward of 0 and go into D. So any state that goes into B gets a reward of 5. Even if you're in B and you go back to B, you still get a 5. And similarly for C and D. So C has no chance of going into B. So either stays in C or goes into A or goes into D, but in all these cases, it gets a reward of 0. So you can solve this equation because you have 4 unknowns and 4 equations. Okay, any questions? So as I said, you can always you can get a Q from a V given the MDP model, which you know. So it's it should be go from Q pi from V pi. So notation is that for each equation here, I write SA R as prime. That is, in state A, you go west, you get a reward of 0, you go back to state A. So instantiating this equation, that's the equation for deriving Q from V. You take the expectation over the R and next state as prime. Then you can see that for Q pi A west, the action, it gives you a reward R of 0 and gamma 0.7 times V pi of S prime, which is next state is still A. And for the east action, you get a reward of 5 plus 0.7 times V pi of B, the next state. And north action, you go back to A. South action, you go to C. Similarly for state B. So yeah, now if you go east or north, you also get reward of 5 and stay in B. So that's how you derive Q from V in this case. So the derivation depends on knowing this particular MDP model, which in this case is always equal, the sum is always equal to 1. So we'll see examples of non-deterministic environments. But here we assume that the environment is deterministic and known. So if the number of states are too large, it may be too expensive to solve the set of linear Bellman expectation equations. Then we can use iterative policy evaluation. So you iterate, you set up initial values and iterate the Bellman equation, just recursion, and then keep track of the data. That is how was the largest difference between the old VS and the new VS, and if it's less than the threshold, you view it as having converged, and then you stop. It's a common trick for solving these kind of equations with a variable on both sides, and then you do recursion, do iteration until convergence. So here's an example of iterative policy evaluation. For this small example, you can also solve it directly, but we just show the derivation for illustration. So episodic MDP with terminal states on the upper left and lower right. And reward is -1 for every transition. That is moving the robot costs some electricity or fuel. So every transition costs the robot a little bit of reward. So this kind of factor is 1 for simplicity. And you have 4 possible actions, up, down, left, right. Environment is deterministic. So if the action would move the agent off the grid, it instead leaves the agent in the same state. So very simple to understand. That is, if you hit the wall, you come back. So let's run a few iterations. Initially, every state has value function v pi s equal to 0 as initialization. And the first sweep for every state, you plug in the equation here. That is, every state has 4 possible actions with equal upper probability. So that's 4 possible actions. And for every action, you have a reward of -1 plus the reward of next state, which is always 0 from any state, starting from the initial state of all zeros. So the first sweep, you get -1 for all the states except the terminal states, which stay at 0. You never update the value function for the 2 terminal states. The second sweep, you start from the result of the first sweep, and then for the states marked as -2, you compute the 4 terms as they're all moving into a next state with value of -1 plus the transition cost of -1, transition reward of -1. So if you look at this state, right? If it goes at this point, if it goes north, it comes back. Goes south, it goes into this. Goes west, goes east. So in all these 4 cases, it always goes into a new state as prime with a value of -1. So these states have the final value of new value of -2. But for the states marked as -1.7, they have so for example, this state, if it goes north, east, or south, it goes into a state with value -1. But if it goes west, it goes into a state with a value of 0. So you have a new term here that's different from the -2 states. And the result is -1.75. And the third sweep, you can, for different states, you can work out the equations. So, as you can see from left to right, the influence of the terminal states, that is the 2 zeros on the corners, gradually spreads through the entire grid. So it spreads, yeah. So the to influence the other states. Okay, any questions on this slide? So the result of policy evaluation, we showed the steps, the first 3 sweeps. They call it sweep. So every sweep, you recompute the value function for every position, every state on the grid, on the small grid world. So after 3 sweeps, you get this set of value functions. And based on the value function, you can get a greedy policy with regard to the value Vk. So in this configuration, all the states are equal. So each position, if you move anywhere, it doesn't make any difference. So the greedy policy is just a random policy. In here, now you have a choice, have a difference at this position. If you move north, you get a higher reward because this guy has a value of 0. Whereas if you go east or west or south, you get a -1 as the next state's value. So the optimal greedy policy is to go north in this direction and could go west in this direction to go towards the terminal states. And after k equals 2, now your optimal policy, a greedy policy, not optimal policy, I should say greedy policy, now is like this. So now at this position, you should go north because you're going into a new state with a -1.7 as the next state. So that's higher than -2 on the right, on the east and south, and also itself. And similarly, after the third sweep, you get these greedy policies. And interestingly, if you iterate for many steps, eventually the values still change, right? You go from here to here, the values are different. From here to here, these are different. This is eventual convergence, but the policies don't change anymore. So it's actually a very common phenomenon that values keep changing, whereas the policy converge much faster than value. So in this particular case, one sweep of policy evaluation is followed by one policy improvement. That is based on the evaluation result. Say, at this point after convergence, you get this new policy, different from your previous policy of random, and then this new policy is guaranteed to be better than the previous policy. There are theorems about it which I did not discuss, but in this particular case, this gets you the optimal policy. But that's just because this problem is so simple. In general, you need many iterations of policy evaluation and policy improvement. We'll see an example later. So policy iteration just adds one more step. We saw policy evaluation. Now we do policy improvement. So while policy stable is not stable, you do an arg max to get the optimal greedy policy with regard to the current value function Vs. To the current, this inside of here, this is the QSA. Except it didn't write it out. It just expresses everything in terms of V. So so you run policy evaluation until convergence to evaluate the value function for a specific policy, and then you improve the policy by one step, and then you go back and evaluate the new policy and until convergence, and then you improve the policy. So here I use the shorthand of greedy V pi as for this equation here. So here's an example of policy iteration. The previous one was too simple. You get the optimal policy after one sweep of policy evaluation plus policy improvement. Now we want to make it more complex. So now we have a single terminal state on the upper left corner. The blue ones are obstacles. That is not obstacles because you can't run into them. Blue states are bad states. With a large negative reward. So you initialize all the values initialize to 0, and you start with a uniform random policy that is at every position you have equal probability of going in each of the 4 directions. So the first sweep of a policy evaluation, you get these values. These are very negative because remember that for the blue states marked here with blue squares, they have a -10. And your policy is random. That is, you're wandering around on the grid with no purpose until you happen to hit the terminal state of on the upper left corner. If you don't hit it, you're wandering around and you're hitting the blue states very often and accumulating a negative reward. So you can see the rewards are very negative, and it's a very bad policy. And then you do a policy improvement based on the current evaluation of V pi s. You can derive new policies. So for example, at this point, north is a better choice than east or south or west, because -129 is the largest value among the other neighbors. And similarly for this guy and this guy, going north is the best and west is the best. So in general, you can see that these policies up here seem to be okay. They're moving towards the upper left terminal state. But these look very strange. They're not very good because they are moving towards the blue states, the very negative states. So that's one iteration of PE plus PI. Now the next iteration, you base on the new policy. Here you rerun policy evaluation. Now the values are much better. For example, here you go from -129 to -1 because now you have a new policy. At this point, you always go north. So you hit 0 immediately. You don't wander around on the grid anymore. So the new values look pretty good, except a few positions. For example, here, this looks like a bad policy. So, and then because you have just done the policy evaluation, after the policy improvement, this policy is okay. Now it knows that going north and get -5 as value is better than going west and get -14 as the value. But a few states, policies still go towards the blue states. These guys are still problematic. So the ideal policy, just from looking at this grid, it should be like this. That should be our ideal policy, just from our intuition. So these policies are still wrong. Now we do another policy evaluation. We got a higher value, -6, from the previous new policy, this improved policy. now it's a -6 here. And then we do a policy improvement. We got a better policy here. Now this guy knows to turn right instead of going up. Another round of policy evaluation, because of the new policy, it gets a better value function, higher value. And then based on the new result of policy evaluation, it gets this guy gets a new policy of going right instead of going north, up or left. Based on the new policy, we perform evaluation again, and because of the new policy of going right, it gets a higher value at this point, plus or -8. So the color indicates a darker color indicates a more negative, lower value. So the policies ideally should point from dark color towards a lighter color. That's the greedy policy. And then you perform policy improvement, and this guy gets a new policy. Now it's pointing right. And then after you do one more policy evaluation, a value function has converged. And then you do one more policy improvement, you get the policy, which is what we thought should be. It goes around like this. And it's the same policy as the previous iteration, like this. So this means that the policy is stable. It doesn't change anymore. So based on the theorems, which I didn't show you, it's an optimal policy. At this point, the value function has converged, but it's not true in general. As I showed you before, policy often stabilize long before value functions converge. So in this particular case, the value function converged, but in general, we don't care about convergence of the value function. We only care about stability of the policy, convergence of the policy. So any questions on this policy iteration? So here's another policy iteration example where the value function converges after almost 10,000 iterations, but the greedy policy converges after 5 iterations. So all these extra thousands of iterations are really unnecessary. So for policy iteration, you actually, as soon as you detect the policy has stopped changing, you stop. So a value iteration is to solve the Bellman optimality equation for state value function with the max A here instead of expectation A for the Bellman expectation equation. So the value function, the optimal policy is output at the end after the convergence of the value function. And in the loop, you iterate until convergence for the Bellman optimality equation. So you are looking for trying to get the optimal value function for every state. So now we don't have a policy anymore. We are looking at all possible actions at every possible state and looking for the best action at every state. So the optimal policy is output at the end of the procedure after convergence. In the intermediate stages, the value functions v in before convergence may not correspond to any valid policy. So only the last after convergence you have a valid policy. So these two actually are special cases of generalized policy iteration. So for GPI, the general idea is to perform evaluation for a given policy and improvement of the policy by acting greedily, taking the argmax with regard to its value function. So there are theorems that show that GPI is guaranteed to converge to the optimal value function V star and optimal deterministic policy pi star. I think it's not very accurate. So it doesn't really care about the optimal value function. Yeah. So policy iteration is to run policy evaluation until convergence, and then improve the policy. Policy, yeah, remember that we had a policy evaluation step where we had a theta as the threshold for judging whether it has reached convergence. And value iteration is to run policy evaluation with one single iteration. And then you improve the policy for one iteration implicitly. So in here, we don't have an explicit pi in the pseudocode. Instead, all we're doing is to update and find the optimal VS. And because we have the MDP, we can always derive the pi from V, but we're not updating pi explicitly like in policy iteration. So policy greedy improvement means that in every iteration of GPI, you always get a better policy pi 2 in terms of the value. In some states, pi 2 will be better, will have a higher value than pi 1. So they always iterate between policy evaluation and policy improvement, except PI iterates the policy evaluation until convergence, maybe thousands of steps, and then does one step of policy improvement, whereas VI does one step of policy evaluation and one step of policy improvement. So it's a more frequent switching between these two. So the computational complexity PI is slower per sweep, also called a cycle, because you need to iterate until convergence for the PE. And with complexity of state squared times action, a number of states squared times action plus state cubed, and requires fewer sweeps, whereas VI is faster per sweep with complexity of a number of actions and the number of states squared requires more sweeps. So these two are just special cases of generalized policy iteration. You can also have intermediate solutions called modified policy iteration. So you run policy evaluation for a number of steps between one for VI and that needed for convergence of VS, the two extremes. You can set this number of steps yourself. It doesn't really matter. Eventually, it's guaranteed to converge. And you can experiment with the number of steps to achieve a best efficiency. So I've been discussing MDP-based planning with the assumption that we know the MDP, we know the R, reward and next state, given the current state and action. But if MDP is not available, we can use model-based learning. That is, you learn an empirical MDP model, you count outcomes as prime for each state action, and then you normalize to get an estimate of T hat, a transition. I should use different notation, and then get reward R hat. And then given the estimated MDP model, you solve it with value iteration or policy iteration. So here's an example. We have a small grid world with two terminal states, A with a -10 as the value function and D with +10. You may equivalently think of terminal state X with a Vx equals 0, and any action from A or D always leads to X with a reward of -10 or 10. So it's equivalent. You can simply view them as terminal states for simplicity. So dark squares indicate obstacles, and the discount factor is 1 for simplicity. So you may have a deterministic environment or a stochastic environment. Whereas if you take a movement, if you try to move in a direction and you actually go in that direction with probability 0.8, with probability 0.1, you go left or right. So the robot, the wheel doesn't work very well. So you're driving in that direction, the wheel may turn in a different direction. Or there may be wind in the environment that blows you to some other direction. So that's the part where the environment is stochastic and is not under the control of the agent. Similarly, if it's blocked by an obstacle in any direction, then it stays in the same state with probability of moving in the blocked direction. So for model-based learning, let's say we have run 4 episodes, B, C, D, and B, C, D, E, C, D, and E, C, A. So suppose we don't know the environment model. We don't know if it's a deterministic or stochastic. We don't know anything. So we're trying to learn a model by executing the policy pi, by counting the transitions out of each state in the observed episodes. So for example, starting from state C, and if we see 4 transitions, C east to D, C east D, 3 of those go to D, and 1 goes to A. So we can estimate the probability of transitioning from C to D is 0.75, and transitioning from C to A is 0.25. So that's how you estimate the MDP. So next, I worked out some examples for policy evaluation. So I won't go into the details, but I hope you can go back and work out these examples by hand to train yourself. So one is for deterministic environment and deterministic policy. One is for deterministic environment. Did I say deterministic? Oh, right. So yeah, I forgot to mention that the updates of the values, you can do regular updates where you always base your evaluation of the equations on the previous iterations value. So V1b is based on V0c, V1e based on V0c, and so on. And you need 2 sweeps to converge. But you can do in-place updates where you can do a 1 sweep in reverse order. That is, after you update C, you reuse the same iteration, the new value immediately when you update V1b. So you don't have a separate copy anymore for the value of V1c. Instead, you update the value of V1c in place and reuse it immediately. Similarly for E. So by using in-place updates, you get the same update, same effect, except you converge faster. So in this particular case, you have a deterministic policy of B always goes into C with the deterministic environment, and C always goes into D, and E always goes into C. Therefore, and initially BCE's values are all 0. So you can see that all the values are going to propagate from D onwards, D to C, and then from C to B and C to E. So if you do the sweep in updating the value function from right to left, from D backwards to C, and then from C to B and C to E, and with in-place updates, you can update these values much faster than if you go from right to left to right and from down to up, because the first few updates are just gonna give you very uninformative updates. Only the last one is very, when you're near the D, then you get very informative updates. Yeah, for this particular example, you can now simply solve the Salad equations analytically and get the values directly. But for larger systems, you may have to use the iterative solving technique. And this one is for stochastic environment and deterministic policy. So now, so for example, if you're in state B and you have a policy that's deterministic, you always move east, but the environment may blow you to north or south. But in this case, you're blocked by the walls, by the obstacles. So with 0.8 probability, you're going to C, and 0.2 probability you stay in B. And in C, with 0.8 probability, you go into D, and the 0.1 probability you're going to A, and 0.1 probability you're going to E. And you can solve the equations to get the value functions for deterministic policy with the arrows and a stochastic environment. And for deterministic environment and random policy, so remember the policy iteration, you have 2 nested expectations. One is to the equations are a little bit different. So one is expectation over all the possible actions based on the random policy. One is expectation over the environment. So here you have random policy of 0.25 going each direction, and the environment is deterministic. So you always have 1 for the environment probability. The last case is stochastic environment and random policy. Now you have actions, random policy with 0.25 probability of going each of the 4 directions, and then the environment is stochastic. So you may have 0.8, 0.1, 0.1 in each direction. So now the equations get messy, but the idea is simple. Yeah, I think this might be a good exam question. So I give you a small MDP and ask you to work out a few iterations of policy evaluation or a value iteration. And then you can see the deterministic environment with value iteration to converge faster. I used in-place updates. So you go from C, and then you use the new value of V1C immediately in updating B. So this is B1C. Yeah, so you plug in the equation for the value iteration and get V1C to be 9, and then you directly use the V1C when updating V1B to get 8. So it converges in one sweep. Finally, stochastic environment in-place update for Q value for value iteration. So B1C, yeah, this is okay. Yeah. So that's all I have for today. So you notice that the Bellman equation here it's from another online slide. It's a little bit different from the what I showed before. I'll unify the notations. But if you read the literature, they write the Bellman equations in many different forms. So this form here. This form here is from the Barton and Sutton book. So sometimes you multiply this inner sum of R and S prime into the this term, and just the sum over S prime and omit the R. So all kinds of variants are possible, but they are all equivalent. This one is the most general formulation. So I think that's all I have for today. Any questions or discussions?
No.
Yeah, so this topic is pretty basic. Just to bring everyone to the same page. So we will go into more advanced research, especially related to autonomous driving later.
I don't know how everyone else feels, but to me it's very much information to take in with these 4-hour lectures. Would it be possible to like split these lectures maybe in two separate days per week instead of just a 4-hour chunk once a week?
That is definitely possible. So let me think.
In fact, I agree with Leon regarding his suggestion. Maybe on 2 occasions per week, it's better than 1 occasion. It's too much for one occasion to have this wealth of information.
Let me ask the others. So let me think. Are everybody available on say Wednesday afternoons?
Yes.
Anyone not available on Wednesday afternoon?
Mondays would have been best for me, but maybe I can rearrange the other course I'm taking somehow.
Zongwa, usually with human-robot interaction, we have a lecture on Monday and Thursday. So if Monday, or let's say Tuesday and Thursday, it will be okay, because if it's Wednesday and Thursday, you have no time to absorb what you took on Wednesday to be well prepared for Thursday.
I see. Sure. Let's aim for Monday, Thursday then. So how about making it Monday, Thursday, 15:00.
That sounds really good to me.
Well,
I agree with that.
Okay, so that is Monday, Thursday, 3 p.m. I'll set the Zoom links.
Do you also have synchronized it with Kali?
Well, Carla is really just helping me for a few lectures. He's not going to teach any more of the sessions.
Okay.
Okay, so great. So I'll encourage you to work out the last examples by hand. Any questions, just ask on the discussion board. So I guess I'll see you on Monday.
Great. Thank you very much for
Great.
yeah,
Okay.
change.
Goodbye.
Thanks.
Thanks.
Bye-bye.
Bye.
Bye-bye.